In a previous video, we have seen how to set up and configure the Red Hat OpenShift cluster to host and serve a large language model. Uh, Now that's done, um, potential way to use this is to actually enhance the knowledge of that model with our own documentation and ask questions about the documentation that we have. So there are two ways to do that. One is fine-tuning the model. Uh, This means like retraining it with the additional information that we want to be known by the model, or by using Retrieval Augmented Generation as a framework that will work with the model in order to provide this new information that the model doesn't have. In order to use Retrieval Augmented Generation, we will need to have a vector database where we will store the embeddings of the documents that we want our model to look at when it provides the responses for us. Uh, so how this is done, if we click here down to this chat video documentations part inside the AI on OpenShift, we see the guide for this. So first one is that we need to have the uh, uh, OpenShift with Red Hat OpenShift AI deployed, GPU node card. So we did all that in the previous video, including the deployment of the Mistral 7B model. Next, we need to create then because we'll use the Retrieval Augmented Generation method, we need to deploy a vector database, and we can use Milvus for this, and the instructions are good here. So taking it like on a lightweight note, what it means here is that the default at this date, the default deployment from Helm charts for the Milvus vector database on OpenShift, it doesn't work exactly as it should, because there are some security issues that prevent it from running it. So in order to bypass those, and to not to bypass those, but to correct the settings, for the Milvus deployment to work on properly in OpenShift, we need to do some changes to that template. And this is basically what is explained over here. So you need first a project where you deploy Milvus, and then you update your Helm resources in your local environment, and you get the OpenShift values from which then you will create a template. So the template can be either for standalone or cluster setup. In my approach, I'm going to do a standalone because it's just for demonstration purposes. And once that you get that file from here by running this command, so it will be called Milvus manifest standalone YAML. You need this YQ tool in order to apply these three patches onto that file. The YQ tool, if you follow this link, it is basically opening up this page. You need to go here for install, and then GitHub page, and then get the latest version that you run in a super user terminal so that you get this installed. Otherwise, if you don't run it as super user, you need to change the path from here to point to your local path so that you can access this. So let's assume that you have that installed, and you run this, and then you need to apply the updated information to your cluster. And that is available through here, right? So the first thing I did is create a project. So no, sorry, the first thing is I logged into the cluster, then I created a project, added the Helm repo, did the update, got the file that I was instructed to get, the OpenShift values, and then I created a template out of it using Helm. I installed in a super user console the YQ tool, and then I applied the three patches. So 1, 2, 3 over here. I also did like a diff to see like what's actually changed. Not many things, but nevertheless, it is important to have those applied. And then I made sure that I'm in the right project, and then I applied the manifest. Now, what happens next is that you will get 3 pods deployed in the Milvus namespace. There are these 3 pods. Wait for them to be fully running, and then uh, we can deploy the UI for management of the Milvus database. And it's just simply applying this command as I did over here. This will create an additional pod in your namespace called ATTU something. Wait for it to be fully deployed and running, and then you can access the UI by clicking on routes. And you click on this, will basically open up a route. The first time you click, it will look like this, so you'll need to fill in your information. The default information, so the username is root and the password is given here. It's Milvus. Recommendation here is that you change the password, so you can do it by connecting to that and then clicking on users and update the password over here. The next thing is that we need to create a collection with those vector embeddings. To do that, we're going to head over to Jupyter Notebooks and create a notebook that will do exactly that. So we will need to install some prerequisites here. Actually, before we are doing this information, we need to provide uh, the username and password to the notebook environment. So how we do that is that inside the OpenShift AI, in the workbenches area where you have your running notebook or stop, doesn't matter, you can click on edit over here, edit workbench, and then environment variables, you can select the type of the environment variable that you want to add. It's a secret with a key value pair, so we add the Milvus password and the Milvus username, and you click update. Now, if your workbench is already running, it will be restarted, right? So this means that you will basically need to, if you use the default images, you won't have this um, additional libraries that you need, so you need to run this pip install command so that you get those dependencies added. And then you can execute this. So the host, if you follow the instructions, it should be exactly this. If you change something in your project name or the way you want to call this vector database, then you go to your project over here and services and vector.db Milvus, and here is your connection and your port. So that's the information that you need to fill in here. These you get from the environment, and then how do you want your collection to be called, where you store your documents. We will use as an example the Red OpenShift AI documentation, the release version 2.6. So this is how you get those PDF files. Then we also want to add some of the web pages that uh, comes with the documentation. So we have the website here, the AI on OpenShift, and get it started and different information. So we combine the two together and create some new chunks with overlaps in between them. And now we have a set of documents ready to be uh, given to an embeddings model to create the vector embeddings. So for that, we're going to use the Hugging Face embeddings model. So actually this class with the default model that's available there, with or without GPU, depending on your settings. You can change here and you can add the model name if you want to use a specific one. Uh, so we'll go with just with the default. Now you could also use your previously deployed large language model, but you don't necessarily need that to create embeddings. You need a small model. And then you define your connection to your Milvus database. Keep in mind that initially we didn't create any collection yet, so by doing this drop all true, we'll ensure that it will create one. So it will overwrite basically the one. So if you had one before, then it will drop it and recreate it. If you just want to add documentation to an already existing store, then make sure that this is changed to false. The documents are added by this method by adding all the splits that we created here, and this can take some time depending on your resources and the number of documents that you want to ingest. Once this function completes, then you will see inside the collections here, you will see your collection added with the documents that you parsed. Okay, you can make a test to see how this works, to get the score, and you get some results over here. All right. So now that we have everything ingested, it's time to glue these things together. All right, so put these things together. We have a new notebook that we need to create. Now here, there are some differences between how this notebook was created and what model was served and where it was served compared to what we did. So follow the notebook that I provided as an example here. It's very similar to that one. The difference is that the following is that the inference server that we have over here, it's basically the one that we obtained after we deployed our model. So this is our inference endpoint. Now, to call the actual model, we need to put /v1 after this, so you can either include it in the inference URL here or later on when you instantiate the model. The model name, it is the folder where we deployed it. So remember that we used in the deployment /mount/models, and then some additional parameters that we want to use for the model creation, as well as the definition or the credentials for the vector database and the collection we created in the previous step. Now, because we use HTTPS request to our inference server, we need and we have a self-signed certificate, we need to get the certificate and add it to the environment. And this is done by using this method. Next, we want to create an embeddings model, right? So remember that previously we used the default one. Now we actually are using the Nomic AI text v1 embedding hosted on Hugging Face, and we create the connection to our data store, including the collection, right? And then we add the prompt to our LLM, and the glue to all of this is done by LangChain. So first we create the LLM instance, and then we glue it all together with LangChain, which is a library, a framework actually, that allows us to easily interact and glue together a large language model with a vector store and make it easy to interact with the large language model like in a chat-based fashion. So we will use this retrieval QA from chain type, which is the LangChain object, provide the LLM, the store that we created earlier, and the prompt. And now we can ask a question, and we get these responses back. And we can also check to see like where does this information come from, like the source of it. So we will look at we have this function that will basically retrieve the source documents from the results from here. And these are the sources from where the large language model took the information to create this response. So that's it.